razor.
Sorry?
Use a razor.
That was bad too.
It's all good.
All right.
Good morning, everyone. My name is Julia Sung from Team New Zealand, and today I'm happy to be here presenting Problem 10, Rayleigh-Bénard convection. The problem statement reads, uniformly and gently heat the bottom of a container containing a suspension of powder and oil, and cell-like structures in form. We are asked to explain and investigate this phenomenon. Here, I define the word gently as having a slow rate of heating of approximately 4.5 K per minute, and I define the phrase cell-like structures as having small bounded cavities that form in the oil. This is an overhead view of the phenomenon occurring. The pink color is because of the mica color used was pink, and because it's flat and reflective, when the oil is moving horizontally, the pink color is reflected because of the light. When it's moving vertically, the color is not reflected. The first stage of the phenomenon, and I'll play the video for you again, is when this one large cell forms close to the edges of the container as shown. Then the second stage is when the smaller cells appear along the edge of the large initial cell. The final stage is when eventually the entire container fills with cells as shown. Moving on to my qualitative explanation of the phenomenon. When the apparatus is set up and the bottom of the container containing the oil and mica mixture is heated, there is a temperature gradient along the vertical axis of the container due to conduction. Under certain conditions, this is an unstable equilibrium because the hotter oil at the bottom of the container is more buoyant and the cooler oil at the top of the container is less buoyant. And I'm happy to expand on this mechanism later in discussion. Therefore, when there is a disturbance in the system, this disturbance is amplified because there is an unstable equilibrium. If the disturbance is amplified, then the warmer and thus more buoyant oil will flow upwards towards the surface, creating cells with warmer oil in the center and cooler oil at the edges. This warmer oil, though, because it spreads out horizontally, eventually cools by conduction with the surrounding oil and the air, and therefore it becomes less buoyant again and it sinks back down. This creates a convection current pattern. Now, how does this apply to our empirical observations? So in stage 1, we can see that there's initially a large single cell forming in the fluid. This forms because the conductivity of glass is greater than the conductivity of oil. So the container walls actually warm up the surrounding oil faster, and therefore the oil that is next to the container walls have a faster local vertical motion upwards compared to the rest of the oil, and I'm happy to again expand more on this in discussion. Then in stage 2, as can be seen, more cells are created along the boundary of the first large cell due to the oil's viscous drag. Again, happy to expand on this in discussion. Eventually, in stage 3, cells fill up the entire container, and this concludes my qualitative explanation. Now let's move on to talk about the theoretical model. So in the process of researching this phenomenon, I investigated the Rayleigh's number, which is a dimensionless number that is prevalent in the study of Rayleigh-Bénard convection. This was derived in 1916 by Lord Rayleigh from the Navier-Stokes equations. So what exactly does the Rayleigh's number represent? This number is the ratio of buoyancy forces to dissipative forces. So it quantifies how much the fluid movement due to density differences from a temperature gradient prevails over resistive forces of viscosity and thermal diffusion. The larger the Rayleigh's number, the easier it is for the Rayleigh-Bénard convection to actually occur. So here is the Rayleigh's number equation. You can see the components of the equation down here. For a surface air setup where the bottom of the oil is a rigid surface and the top is free air, the critical Rayleigh number is 1,100, and this is again derived from Navier-Stokes equations. If this number is met or exceeded, cells will form, and if it's not met, then cells will not form. Therefore, through rearranging Rayleigh's number equation and utilizing the critical Rayleigh's value, we can derive a quantitative model that can predict the temperature difference required for the system to start forming convection cells. Here are the assumptions of the model derived from Rayleigh's number. So I'm happy to go into these more in discussion and justify each of these assumptions. Now here is the experimental setup that I have used. So I have a hot plate, and on top of the hot plate is a pure aluminum block, and then I have an aluminum saucepan with sand in it. The purpose of the aluminum block between the hot plate and the saucepan is through conduction, it can evenly heat the saucepan, because when the hot plate was tested on its own, there was some uneven heating in the surface. The purpose of the sand is to have a layer that is able to slowly and gently heat the beaker instead of it being a fast and rigorous process. So for my experimental method, what I did was I first heated up this triple layered system, then I placed the beaker with the oil and powder mixture onto the flattened surface of the sand, and I immediately tracked the two initial temperatures. So one is at the very bottom of the liquid and one is at the surface that is slightly above the surface of the oil. This was because and then I removed the temperature probes immediately after that initial measurement. The reason for this was because the temperature probes are around 2 millimeters thick, so I found that they did affect the phenomenon to an extent, and I can again expand more on this in discussion. Therefore, when the phenomenon had occurred, I again inserted the temperature probes and took the final measurements, and I extrapolated this as a linear curve, and I have justification for why I did this. Dependent variables that I've investigated. So firstly, I've investigated the temperature difference required for the convection cell phenomenon to begin. The phenomenon beginning is defined as when the second cell appears, not the first large initial cell, because the formation of that is basically spurred on mainly by the conduction of the glass balls. The second dependent variable investigated is the number of cells, or the number of cells per unit area. I used the cells per unit area only for experiments where the radius of the container was actually changed, because otherwise it would simply be proportional. Cells were identified as actual cells if they had a clear dark boundary of vertical oil movement at the edges. Now for the independent variables I have changed in my investigation, we have depth of oil L, physical properties of the oil K, I'll expand on this later, and the radius of the container. So on to my first independent variable that I've experimentally varied, the depth of the oil. Using the Rayleigh's number model derivation of the theoretical model, this is what the theoretical model predicts will be the relationship between depth of oil and the temperature difference required for the phenomenon to begin. And these are my experimental points to the theoretical model. You can see that generally it is a very good fit, with the temperature difference required decreasing as the depth of oil increases. This occurs because although the buoyant acceleration at a given temperature difference is constant, in a deeper fluid layer, the rising warm oil does have more vertical distance to accelerate through, and therefore it has more speed that it accumulates, and therefore a greater kinetic energy. So this increases the chances that the motion will overcome the viscous and diffusive damping that restricts this motion. Additionally, increasing the depth, it just generally means a larger vertical portion of the fluid becomes unstable, and therefore is able to participate in this convective motion. So together, these effects mean that as the system becomes more unstable, and at lower temperatures, even when the oil is deeper, which means that it's easier for this to occur in deeper oils. However, if there can be seen, there's a small discrepancy with the theoretical model because the model slightly under-predicts the temperature difference required for the cell to form. This is because the critical Rayleigh number is when the buoyancy forces are able to overcome these dissipator forces, and therefore, even at the critical Rayleigh number, it does take time for the cells to actually form and to be able to be visualized. Now, the effect of changing depth of oil on the number of cells, as you can see, as the depth of oil increases, the number of cells in the container decreases. This is because fluid optimizes and it prefers a certain aspect ratio of cells in order to minimize energy losses. And what this means is, if cells are too narrow, as in if the cells form like this rather than this, it means that they firstly don't transport much heat, and secondly, suffer a lot of viscous drag. And this obviously is not efficient for its energy purposes. What this means is that when the cells are too narrow, this is not preferred, and therefore cell size actually increases with the depth of the oil. And therefore cell number has a negative relationship with the depth, which makes sense. Second independent variable, the physical properties of the oil. So because it's not possible to independently isolate these three fluid-specific properties. I've grouped them into a constant K, so K is B alpha over beta, and therefore this model can be fitted onto the graph. You can see that the model does predict a proportional relationship with the K value increasing and the temperature difference required also increasing. This is my data fitted to this curve. And this makes sense because the numerator of K is representative of the dissipative forces, while the denominator is representative of the buoyancy forces. The greater the numerator is over the denominator, the harder it is for convection to occur. Here's K value graphed over the number of cells in the container. You can see that if the properties of the fluid are more dissipative, as in like you have honey instead of water, then smaller perturbations are going to be dissipated more easily, and therefore only larger perturbations are able to be actually amplified into these convection cells. My third independent parameter, the radius of the container, this was done by just changing beakers. So as the radius increases, the temperature difference required for the phenomenon to begin decreases. This makes sense because the side walls of the container have an edge effect. There's two ways in which this manifests. Firstly, cells require horizontal movement to form. If the radius is small and this is restricted, the fluid is going to slam into the walls and lose momentum. Secondly, if walls conduct heat laterally, and this means that they smooth out the vertical temperature gradient. Therefore, this qualitatively makes sense. The effect of increasing radius of container on the number of cells, we can go over this in discussion again, but a larger radius means that fluid is able to move more freely and have a better aspect ratio. And yeah. Problem statement, I believe I fully explained and investigated the phenomenon. The conclusion is that convection occurs, and that's shown through the mica powder. This model works, fits very well with data, and I've been able to justify any deviations from data. Here are my acknowledgements. Here are my references. And thank you for listening.
Thank you.
Thanks for the presentation. So first question, do you calculate the Rayleigh number after the cells started to emerge? The Rayleigh number
The Rayleigh number was calculated
after the cell emerge. When the cells started emerge.
The Rayleigh number was never measured.
Okay, I'm going to discuss later. So second, do you think the surface tension of the liquid is very important?
I don't think it's very important.
Yeah, okay, thank you. So what is the highest temperature that you use to do experiments?
42
42. Yeah, okay.
Celsius.
Yeah, okay. Do you consider evaporation during the heat up process?
No.
No. So your top, you do have cap on just the air.
No, but I believe that evaporation is significant enough to consider.
Yes, okay. So, I think we discuss later. So what is the temperature of your side container? Because you have mentioned about the reason of why this was started from side, the temperature of your side container.
The temperature was not measured, however, it is more conductive, therefore I assume that the temperature would be greater than the oil inside the container.
Just like a room temperature?
Because if the whole system was heated, there's no way that that can remain.
Okay, so what is the viscosity of your oil that you use?
The fluid values I can show.
Or
Yeah.
you can discuss later. So for the next question, is really I see that you're a picture of your center of cell. I think that's great. So is the center of the temperature of your whole distribution of your cell is the same, or like middle part is higher?
Using FLIR, I believe that the
This is a whole petri dish
so
or
this
cell.
is the sand. So the surface.
I mean the
of the
cell. I mean the cell.
Oh, the cell. That was not measured.
Oh, okay, I got it. So again, do an experiment to change the length of it, the height of it. So is the cell's area always constant? Or-
No, but I have the data for that. I can explain it to you again.
Yeah,
in
sure.
discussion.
Okay, so it's a fat surface of your cell, or there's some depression, because I've seen there's a dark side in
Okay.
your cell.
I'm afraid of stopping.
Yeah.
Can you write that down somewhere? Just write socks.
Laura. I'm an opponent from Team Taiwan, and today I'll be opposing our intent graded but not convection. Here is the problem statement. Uniform and gently heat a bottom of the container containing a suspension of powder in oil. Cell-like structure may form. Explain and investigate this phenomenon. So the reporter actually do a great job to control the uniform and gently heat. But here there's some convection. My conclusion here will be some convection that the effect will causing the convection occur and the energy transportation during this whole process. And also the cell-like structure. You see the reference characterization of cells such as area, size, or shape. And the reporter have to do a great job to discuss the size. And for the main form, I believe that there is some critical condition of the formation of cell. Here's the overview from the reporter. The reporter had a clear explanation of how the radiographic cell actually appeared. So first it will appear from the edge. And also it's due to the vertical temperature gradient change during this whole process. And also next process, the center of the cell started to force upward. And for that stage, the whole container will full of cells. And here there are 3 stages in here. I think that the reporter could mark the temperature during this 3 stages to clarify each stages of which each stage the cell will start to emerge from edge and from center. Also, I think the report should discuss on energy more because it's about the convection to transportation the energy during this whole process. Also, I feel by here the report has a good observation of cell structure to see the different size and different areas. And here's the quantitative part. Reporter use a real number to calculate out which condition that the cell will start to emerge, and the critical number for here is 1,100 with a condition is surface and air setup. And also it consider buoyancy here, but the reporter said that the surface tension is not very important, but I think we'll decide the cell's geometry, so I think we'll discuss later. Also have solved all the liquid conversion through Navier stokes. And here the reporter have considered effect of viscosity. Also have used some parameters to change it to see the difference. But here I think the reporter should consider evaporation during the whole process because you didn't have a cap on here. And also lack of data deviation analysis. Some diagram here see that the real line still has some gap between it. Also, I think that the critical real number will not be a constant when you change the condition of the experiment. And here's the experiment of our report. We already have 3 parameters here. I think it's a very good job. First one is the different depth of oil, and it will affect our temperature differences required for cell to 70.5 to 1 degrees. And also the cell size will increase with the depth. I think it's a great observation on it. Also with a greater K, you will have a harder convection to let the convection start. But here I think the reporter could compare with the different temperature with the cell's characterization, because I believe that with a different temperature, it will have different size of cell and other geometry phase. Also, at the fitting of K, I think is reported. But I think the reporter also do a parameter about the different container, and with a large radius, they will have a less temperature in here. But here, I feel the reporter should use a PF5 method to see a velocity field in the convectors for a convection cell to have more clear explanation about how actually the relationship between the radius and the cell number. And here I'll discuss this point out how we report it later. So first I would like to discuss cell formation, the basic observation about how the cell and other geometry fits. And also to discuss experiment control, because in here I believe that the experiment control is very important to let the cell form. And the report mentioned that if it change, even if you put a small sensor in here, it may affect the cell formation. Also to discuss the cell-like structure, just discuss more characterization, and also discuss the reference parameters that the reporter did. And now I will require the reporter to have a discussion. So can you first take her page about that you have built experiment to not your experiment video.
Oh,
yeah.
This one.
Yes. Oh yeah, in here, so yeah, see that you use a sand to heat up the container, so including the side. You
the sand was flattened at this level.
Also, in this side, you don't have heated up.
No sand.
So, can you tell me why the cell will start from H?
Oh, okay.
Yes.
So
because
so even if this is sand
yes.
and this is flat and this does not, the sand does not directly touch the sides of the container.
Yes, of
There
course.
is still conduction of the glass, that is, heat transfer is going up this way along the side of the glass, and that's because the heat conductivity of the glass is greater than the heat conductivity of the oil. And
yes,
that means that
course.
when this heat is just generally heated,
yes.
this will become faster than this.
Yes, but I partially agree with you because I think that because you only heat the bottom, so inside in here, I think that it's like a relative relationship. The liquid temperature in here is much different between here because you have said that the temperature in here is much lower, right?
The temperature in the
On the
glass
side of gas is much lower than the downwards.
yes.
Yes, so I think that is due to a bigger temperature difference that will cause in the H from side. But I still I agree with you about the adiabatic everything. So I think
Do you believe that at a certain height, the temperature of the glass is going to be lower than the temperature of the oil that's right next to it?
yes, this is what I mean.
Could
I think there's much big difference temperature between liquid and the container. So this is why the H will start to emerge from the cell. Yes.
So to clarify, do you think that the oil temperature is going to be larger?
I mean, yeah, because you're heating up the oil.
I believe that is wrong. I believe that because there is that conductive effect of glass, which is faster than the conductive effect of oil.
So you think that the side of the container is much higher than oil?
Not much, but it is higher. I believe so.
Do you measure it?
I don't have measurements, but I do have values. So the conductivity of glass is around 4 times higher than the conductivity of oil.
Yes, I agree. I agree with this. Okay, so we both agree that it's due to a different conductivity, right?
Yes.
Okay, so I think we can. I think we don't agree. Also, next temperature deal. Yeah. So when your the cell started to emerge, you can see that there's a significant. Okay, just fast forward to let the cell happen. Okay, so in here. So is that right? Because you see that there's a different color between the center and the H. So I'm correct that can I say that there's a depression in the center of cell?
No, you cannot.
So you think that it's a fat one? In a fat surface?
I believe that there may be a slight depression, but that's not too significant in this experience.
But I think this is the one characteristic about the cell-like structure.
Yeah.
So for my opinion, I think that okay. So the convection is started like this, right? The hot field is go up here. So I think that due to this here has a velocity field in here, the pressure is much lower inside. So there is constant pressure between the center of the cell. So I think that you could next time you characterize this the depression in here. Yeah.
So I personally disagree with that statement. What I think occurs when the hot fluid reaches the top of the cell is that it simply has to move out horizontally because the displacement of the water from the bottom is going to have more oil being pulled down to it. And I also believe that there is an effect of surface tension, but I believe that effect is actually different because the surface tension of hot oil is going to be lower than the surface tension of cold oil. Therefore, if the fluid rises upwards,
so there is a difference between here because in here is a hot go up there, but the cold will go down. So there is a difference between here. So I think that there is a called depression in here because you have said that the temperature is start at this. And about the coldness, if they go down, I think it's the age of the cell because I think this is one cell of your definition. So the age in here is the cold liquid go down. So I think your mean is like this. But now I'm discussing about the middle parts. Because you can see that there's light intensity difference between here.
yes.
Or can you explain why there's a difference?
Yes, I can explain that. So basically, I have a slide on this actually. So mica powder, there's two properties of mica powder that I'd like to discuss.
Yes.
So firstly, mica powder is flaky, and by that I mean it has a wide dimension like this and a thin dimension like this, and that makes it able to actually be aligned with fluid flow. So it's never going to go this way.
Yes.
It's gonna go this way or this way. And what that means is because, as you can see, the mica also has reflective surfaces. When the mica, the horizontal movement of the oil is flat, it's gonna reflect light and become pink. So the horizontal movement is pink, the vertical movement is dark.
So I think just due to different reactive surfaces.
Yes.
Okay, I'm not done with review. Okay, character page 21 about experiments. The 21, page 21, yes, thank you. Okay, you have changed the different depth of oil here. I think it's very great. But can you tell me that with a different depth of oil, is the cell formation all constant, like the cell's area or cell size?
So cell's area and cell size is basically, I think, more referring to this side. So as the number of cells in the container.
Yeah, but it's a number. I mean a size or like a shape. Because I think that with too much depth, it will cause a turbulent flow during when you heat it up. The cell will very like irregular. But if you just heat the low depth, the cell will just like have a regular shape. I mean that with different depth will have different shape.
Yeah.
Will have.
So I do agree that if number of cells decreases, the area is going to change as well.
Yes.
For the turbulent flow, I did not specifically investigate the turbulent flows that I've observed. I do have a video that I can show you if you want, but I believe that is something that's not part of
Yeah, of course, based on your discussion, but I think that you can also look the this is also one part of characteristic of the cell. So I think there's much different because also you have a character page about the Rayleigh number
Yes.
part page with the one below 11 and 0.
Was it this one?
Yes, of course. So in here you said that a critical Rayleigh number is 1, 0.
Yep.
Right. But I think that just as the turbulent first, when you have heat it up like too much, when like Rayleigh number become like this. So what will happen?
So this Rayleigh number, it's the critical net Rayleigh number.
Yes, I know the critical number that the cell started to emerge. But I mean that what if the Rayleigh number is like 10 times bigger than this?
That is not relevant because the Rayleigh number, so the condition, the critical condition is always constant. So it's the Rayleigh number at which the cell was formed. Of course, the Rayleigh number does vary as temperature increases. But
yeah, I kind of disagree.
could you explain why you disagree?
I agree with you with that the 100 in here this number is a critical number that it started to emerge.
Yep.
But I think that you should discuss what if the Rayleigh number keep going up, because just I mentioned there's maybe some different cell formation here, and you also mentioned that the depth of the cell have different cell like shape. So I want what if this one is just very
So
big
this
enough?
video is of like very intense heating. This went up to around 200 degrees Celsius. As you can see, as the Rayleigh's number
Yes.
increases, you
Yes,
have
well,
this
this is what I
incredibly turbulent flow. I did not in particular investigate this effect because I thought it was less significant.
Okay, but this video is just what I mean. Because I think this is also one part of the cell-like structure. So I think
I believe that the cell-like structures here are much less significant in the discussion of Rayleigh than not convection.
okay,
Because this is
okay, I think we did.
okay. That's okay.
About the K, you have changed
Yes.
the K, yeah.
Sorry.
Sorry, can you repeat container part? Sorry.
Containers?
Yeah, about
Okay.
container. So you have explained that when you change the container.
Yeah.
Can you explain one more time? Because I can't read. So you think that the convection will just hit it at the side, or?
So I believe that when the radius of the container is smaller, then
Yes.
there's limited horizontal movement of the cells. Horizontal movement.
Movement.
So the oil wants to move horizontally when it reaches the
So
top.
do you observe the velocity field during the convection? Because I don't know what the horizontal movement is.
So by horizontal movement of the oil, I mean when the oil rises up, it has to go somewhere. It can't go up, it can't go down, it's gonna go sideways. That's just convection. And
Yes.
what I mean is if they need this horizontal space to form, if there's a wall that's restricting this space, then they are going to slam into the wall and they're gonna lose momentum and they're
Yes,
gonna lose energy.
yes, I agree with you what the reason about because due to the shape. I think you can use the PF method to put a particle and to shine a laser in. You can see the actually velocity field, so you can know when the horizontal movement is.
That would have been very
Yes,
insightful. I
yeah.
agree with that.
Okay, so about K. So here both change the viscosity or does
So
the three both change? Yes, can you change about data that you change the K?
So K, because the fluid-specific constants of the oil are
Yes.
not able to be isolated, I did
Yes,
group all of
yeah, I
the
agree.
fluid-specific constants into one constant K.
So how about why the lyric part is just only in here? Why the other one here you don't have a lyric line?
Sorry, could you?
Why the lyric line is just stop at here? Why here is no lyric line?
Oh, that's because the radius and the depth was, so the length was.
Okay, sure. Okay, thank you.
Thank you very much. Some after comments.
Okay, after discussion with the reporter about experiment control and about the reporter put it on the stand bracket at bottom, and I believe that is uniformly and gently heated up. And I believe that that will be lower temperature due to the conductive of that. We will both agree with this. And also the possible differentiation is there of cell. Because I think there's a significant different color intensity in the center of cell and edge of cell. So I think that according to the surface tension, there is some slight diffraction will be present for all cells. And also the depth of oil. The shape of cell will depend on the oil depth due to the turbulent depth. But the reporter didn't investigate this. And also the critical Rayleigh number. The higher Rayleigh number induces the turbulent flow. The reporter had do experiment, but the reporter, I think this is also the one characteristic of a different cell life. And for a different K of a liquid, I think there should be no slip condition at the boundary of container, but both appraisal could use the PF5 method to see the actual velocity field during the convection. And this is all my complete summary of my discussion.
Thank you. Questions of the reviewer?
Yes, thank you very much for this discussion. So first, can you actually predict the number and size of cells in your container?
Yes.
Based on your model? Okay, thank you. So what's the Prandtl number of the oil you use?
So the Prandtl number of the oil specifically?
Yes.
Um,
And with a function of the temperature. Or like what oil did you use?
so Prandtl number depends on momentum diffusivity.
I understand, but like which oil did you use? And
I used 4 oils, so that was
just the old type, was it silicon oil or?
these 4 types.
Alright, thank you. Now to the opponent, you mentioned something in your clarifying questions about an experimental verification of the Rayleigh number. Could you elaborate on that?
I mean that because the critical Rayleigh number means the starter immersion cell. But I think that we need to calculate it when you start to have a convection.
Okay, thank you very much. And do you believe that this rounded container shape at the edges actually has an effect on the convection?
The shape, yeah, of course. The
Okay,
shape
and
will affect.
what would that effect be?
I think it will affect the side of it because it will affect the which
Alright,
place
thank
will
you.
start.
What would the
convection.
reporter say to that? Does this rounded edge have an effect?
It does have an effect. It's minor, but I can explain it to you.
Yes, actually, that's nice. Now, what were the conditions to assume that the critical Rayleigh are 1100? Just the air and
So rigid
oil.
bottom, free air.
Alright, thank you. And when averaging the cell size, did you take into account the edges or did you dismiss the edge effect?
I'm not quite sure what you mean by the edge effect of the cell number.
The edge effect when, I will mention it later. So, does changing you only changed the Rayleigh number in essence because you changed parameters of Rayleigh. So do these values mean something differently when you change the height or the parameters of the oil?
So the height and the parameters of the oil, they are factors of the Rayleigh number.
Yes. And like what exactly did you fit for K? What is K in a physical sense, the value of K as a parameter characteristic?
K is thermal diffusivity times kinematic viscosity over the thermal expansion coefficient. These are all fluid specific values. The numerator is the dissipated force, the denominator is the voice.
Thank you very much. And what role does surface tension play in this phenomenon, as you mentioned in the discussion?
I think it will cause the top shape of the cell.
Okay. Do you agree with that? No.
I don't believe so.
Okay, so you agree that the driving force is just that the particles need to go somewhere else?
Yes.
You disagree?
Yeah, I disagree.
Alright. Now, also, could you briefly justify assuming that heating to be linear?
Yeah, so that is just experimentally justified. And when it started to deviate at the top, so this was the top of the temperature changing, this was the bottom temperature changing, and I did fit a linear line to this. When it started deviating from the linear line, I just stopped.
Okay, and what were the Rayleighs you investigated, Rayleigh numbers?
Sorry?
What were the Rayleigh numbers you investigated, the range?
There's no, I've isolated the Rayleigh number to be K and.
All right. Thank you.
and I'll be reviewing problem number 10, Rayleigh connection. So first, let's get into the evaluation of the problem statement, of course. So uniformly and gently heat the bottom of a container containing a suspension of powder and oil, for example, mica powder and silicon oil, and cell-like structures may form. Explain and investigate this phenomenon. First, let's get into the evaluation of the report itself. So we had the buoyancy force explanation and the conductivity of the glass was considered. The boundaries were investigated as the critical Rayleigh number, assuming that the top there was like shear surface, and there was also a discrepancy analysis. For some parts to improve on, we had the lack of experimental comparison between theory and experiments. There was little qualitative analysis of the cell-like structures themselves, in my opinion, and there was little own contribution to the theoretical model, as it was only the definition of the Rayleigh number that was investigated. For some experimental parts, we had the aluminum block for uniform heating with the sand. I really liked the idea. And also, as I said, the sand for the gentle heating specifically. Also, there were some parameters that were varied that were relevant to this problem. For some points to improve on, there was no continuous temperature measurement. However, the reporter explained that was due to the tracking that actually interacted with the formation of the cells. And then also the shape of the container was not considered specifically, so we had a change in the radius, but not any other aspect ratios. Also, there were only little data points to verify some of the graphs that we saw. To get into the discussion and the opponents' conduct here, we had a very nice summary of the report. And we pointed out that the uniform and gentle heating was given in the experiments. Also, they suggested PIV for the velocity field, which I very much enjoyed. They discussed the qualitative aspects of the cell formation first, and then he asked about the heating of the container walls, which is a fair point, I believe, but also the reporter, of course, had an answer to this. There was he introduced the turbulent behavior for the high Rayleigh numbers, normally at a range of 10 to the power of 9, and pointed out the fitting parameter of k and what exactly that is. Next up, he mentioned, so points to improve on, he mentioned the measuring of the Rayleigh number. That was first not clear to me, but then in the clarifying questions, I got what he was trying to say. Then he focused too much on the less significant points like evaporation, which don't really seem to affect as much. And there was little discussion about the container shape specifically and what the aspects of the container actually contribute to this problem. Next up, they did not bring up the lack of comparison, and they did not question the linear temperature assumption. To evaluate the discussion further, we had the heating of the walls, where the reporter said that the heat conductivity causes the heating of the glass. Obviously, we agree with that. However, also this causes inverse convection, so this could have been a topic. Next up, we had the cell formation itself. So the displacement of the surface liquid by oil coming from below was the answer of the reporter. And the opponent believes that surface tension was the main cause, however we agree with the reporter, as displacement is the most relevant parameter here. Next up, the mica powder is used since it aligns with the oil, it has the flaky structure. And we totally agree with this point. It's very nice for the tracking and to actually see the phenomenon due to the optical components of this. Next up, the Rayleigh number. The reporter calculated the critical Rayleigh number for the specific setup, so this is very relevant threshold. And the opponent just questioned what would happen for high Rayleigh numbers. Obviously, we'd like to see the higher Rayleigh numbers investigated, even chaos or turbulent flow. However, we believe that this critical Rayleigh number is the most important key factor. For momentum loss at the walls, we have the oil bumping into the walls and losing momentum, and we agree with the reporter here. Thank you very much.
Thank you very much. Final remarks of the reporter.
Hello, so giving my final remarks of this slide, I believe that overall it was an excellent discussion across all three teams. Firstly, the things that we covered in discussion was we expanded on the qualitative process behind the cell formation, so even when the weaker sides were heated, and I think I definitely did clarify that the effect of the different conductivities in the oil and the glass is what causes the very first cell to form. I believe this was justified from my perspective. The opponent didn't disagree. I did not agree with his opinion. We looked at the video of the phenomenon occurring, and we clarified the origin of the different colors. I believe that that's due to the properties of the mica powder. I did not agree that there was going to be a deep depression in the center of the oil. Some things to clarify, I did not fit any parameters, so K was just simply literature values. And we also did go over some expected deviations from theory. So for example, the depth of the oil versus the number of cells formed, and this deviations I believe were fully justified from my perspective. We also investigated the effect of like having a higher Rayleigh number. I showed the video of the very turbulent flow, but we believe that this is post-critical behavior of the system. So what the system behaves like when the actual convection cells are constant in the container. I believe that is the most important factor and the most critical factor that I needed to investigate for this problem statement. But of course, there would be interesting things to investigate in terms of chaos in higher Rayleigh numbers. We also agreed with the opponent's suggestion that there could be a different way of measuring, speeds that occur at the edges of the container. We thought that this would be, an improvement operator. In conclusion, I believe that the setup of my experiment was able to demonstrate the phenomenon. There was very relevant parameters such as the depth of oil, the oil properties, and the radius of the container. I believe that the trends and the deviations from the model were all justified in my context. And I also believe that finally, the modeled quantitative fit had a great comparison and great agreement with my data. Therefore, thank you so much for this discussion.
Thank you. There's some time for some jury questions. Can we move the screen again? Sorry. Back and forth, but then we'll see the reporter's presentation. I have a quick question to slide 21 to the reporter. So for this model, you have delta, you have the viscosity, but the viscosity of cold oil is much higher than the viscosity of hot oil. So when I start, you notice that when you stir, for example, honey or something when you heat it. Did you account for this in any means, or you just took the room temperature value?
So the business approximation, which is the approximation that accounts for density and therefore viscosity, it accounts for the buoyant forces. The density difference is changing in the buoyant forces. It doesn't account for restrictive forces. We believe that the buoyancy is the driving factor of this phenomenon.
So the decrease in viscosity with increasing temperature is not relevant for this.
We believe.
And we'd like to just add that the highest temperature difference we ever found in this phenomenon was 20 degrees, and in that scale, perhaps the viscosity would not be changing much.
Yes, sorry.
Yes, I would like to ask the opponent, during your speech you have talked about the use of PID. Can you explain the meaning of the PID shortly?
Okay, so the PID formula is about particle, you can put some particle in here, and use a laser to shine at it to the liquid, so you can see the particle, how it moves actually. So you can know the velocity field about the particles.
Thank you so much.
Also for the opponent, during one point you mentioned pressure influence on the
Depression of a yeah.
Could you really quickly give us an estimation how that effect would be, how significant that effect would be?
I think that due to the convection, hot liquid will up at here, so it will cause a lower pressure in here. So also about the rotation, like a Maragoni effect, so it will cause a depression.
Like spottable depression, like I can see the depression. That's your opinion, right?
Yes.
Okay, thank you.
Yeah, also you chose 4 different kinds of oil. How did you choose them? Why did you choose?
They were just the oils available which had 100% purity factor, and I believe that would make literature values more accurate.
Simple question to the reporter. For the upper temperature, that's a thermometer in air, or how? What is the upper temperature?
So that is the thermometer placed right above the surface of the oil, so it's not touching the oil.
It's the air temperature.
Yes,
just
that's the
above.
free.
Okay.
Let me ask you, if you have time, the reviewer. So in your presentation, you said that this discussion about the pressure is in the category of irrelevant parameters, right?
The pressure.
Pressure.
In which sense specifically? Oh, the dump that we had that we discussed?
Yeah.
Yeah.
So you think that effect is negligible, right?
Yes.
Okay, thank you. Do you have any explanation why?
Of course, because the magnitude of the pressure difference is insanely small, so you wouldn't actually see it when you perform the experiments. That would be.
Thank you.
Can you again, it says slide 21. Can you again state your opinion why you have the deviation at larger oils?
Yeah, so the deviation, I believe, is caused because at the critical Rayleigh number, that is when the buoyancy forces are able to rise up, and that means that there's still time that takes for the Rayleigh-Benard cells to actually occur. And because there's a linear heating of the system, then there has to be, when the phenomenon occurs, there's going to be a slightly over measurement of the temperature difference.
Okay, and just to cover, this is the best fit line of the shape, or is this?
I have no best fit lines in
so it's
my.
the K inserted from the.
Yes, all of my lines are quantitative.
Any further questions?
Maybe really quick one. For the reporter, so you approximated that the surface of the liquid is at constant temperature, right?
No, I approximated that the surface of the sand is at a constant, therefore it's uniformly heated.
And on the top?
I did not measure, but it would not be constant. It would not be constant.
Okay, thank you.
Okay, I think we're out of time. Thank you very much. Everyone done?
Yep.
Okay, then I ask you to show me the grade for the reporter, please. Five, 7, 7, 6, and 7. Next grade for the component, please. 7, 5, 5, 7, and 7. And final grade for the reviewer. 6, 7, 7, 8, and 7. Excuse me. Okay, we have 3 sevens and 5. Let's, as always, start with the high grades first. Can I ask one of the 7s to volunteer? You have to pick one. Look.
Okay. Fine. So, few things were not totally clarified during the presentation. For example, this Bottinelli's approximation, because it was stated that you completely disregard the difference in density, which was later clarified. Overall, I think you had pretty nice experiment done in a systematic way. The biggest problem for me was the lack of theory, of theoretical comparison between, in a way, something more systematic. You basically covered only critical Rayleigh number and number of cells per unit area. So, and I also couldn't totally clearly see what was the theoretical prediction for a number of cells per unit area. So that's why I gave you 7. It would be even higher because your experiment was really good. That's it for me.
I was on the low side, so I like that you can produce the phenomenon. You see the cells. Also, like the qualitative explanation of the onset is perfectly fine with me. However, I have several issues with the theoretical model and also what you actually are or what you are observing. So for one, you cannot plot delta t as a function of depth in the Rayleigh number. The Boussinesq approximation assumes there's no variation in the viscosity at that temperature. So it takes the viscosity value at that median, the average fluid temperature, and does not consider variations in that around this median temperature. So the correct quantity to plot is delta t over the viscosity, because the viscosity does change significantly if you heat it even by 10, 20 degrees. So you do see a drop in viscosity. So that means the onset is lower than you would expect if you take the room temperature viscosity for this critical Rayleigh number. I also think you see partially Marangoni effect and not Rayleigh effect, because at very low surface, Marangoni is relevant if the oil level is very low, because then the surface tension effects play a greater role. And I think at the very low oil depths, you actually see Marangoni and not the pure Rayleigh convection, because you can see Marangoni-induced convection, which is also fine. It's part of the effect, but you do not differentiate between that. And then also I think the scope is a bit limited. That's a point I mentioned. There's also it says cell-like structures may form. That means you need to describe when does it start and when does it stop. There's also an upper limit, right? You had it in the video. At least tell me qualitatively why does it end at one point. You said it's turbulent, that's perfectly fine, but like try to integrate it in the presentation because you observed it. So then try to bring that into that presentation. So my partial grades was 2.5 and 1, which gives 1.5, which I found 2. All right. For the opposition, we have 3 7s and 2 5s. Again, we start with one of the 7s. Can I ask one of you to give a comment on that?
First, of course, 1.3, 2.2, 2.0, now subtraction 6.5 ammeter. Overall, I tell that the opponent knew what he was doing. He had a lot of relevant remarks. It's a good position.
Okay. We also have 2 5s.
I have given 5, so maybe I will explain. At first, you have asked at least twice about things that were already clearly shown on the presentation. The first one is the temperature measurement, and it was also brought later on that how it was linear according to other measurements that were shown in the attendings. You also asked about the size of the cells, and also this Rayleigh number when it goes to the moment when we have not linearity in the flow. I mean, this another presentation, another movie that the reporters show when the difference temperature is high, so it's a lot of cells going on, but it's very fast. So it was also explained. You during the discussion you also talk about the adiabatic change. That was also asked in the discussion. I did not want to go to details during the jury questions, but it was also something that you mentioned but did not go further on. So that's my reason for the grade, and I give you 1 for the question asked, 2.25 for the opposition. That was the first part of your speech, and then the discussion 1.25 and run up to 5.5, so round it up to 5.
For the review, we have a single 8.
Yeah, again, I like the review, she knew what she was talking about. This, I suppose, I'm a little calibrated higher, so that shouldn't be, I shouldn't excuse myself too much for that. 1.6, 2.4, 1.5, 1.5. Overall, I'm pretty happy with the lesson.
I was a 6. It was definitely not a bad review by no means, but I don't think it was an outstanding review either. For example, like with the questions, like you ask about the first question is brilliant. If the number of cells is predictable, she says yes, which doesn't really make sense. But then you don't. But then you ask about the Prandtl number, for example. Like she doesn't have the Rayleigh number calculated. What is the Prandtl number? Like why would she have the Prandtl number? It's like it's not, or you cannot show me what is. It's not the biggest issue in this report. And I think for both the opponent and the reviewer, I mean, I think you failed to fully highlight the issues in the presentations which were there, and I think that is basically why I ended up at 6. So you get 1 for the question, 1.5 for the review of the report, 1.25 for the review of the opposition, and 1 for the discussion, which ended at a 6. Any questions from your side? Else we're still here for a few minutes if you want to talk about anything. And if not, I would like to thank you all for a very interesting fight this morning. And I hope to see you at a good afternoon. Thank you very much. Thank you. Thank you guys.